Well, this is the last section of this tutorial, and in this section, a way for the simulation or implementation of fractional fuzzy inference systems in the Matlab environment is explained. The implementation of FFISs in Matlab software may be done through the use of the mfile ffis.m. This Matlab mfile function is open source and in the form of a package is available for free on the Mathworks website. The package includes the following 4 files: the help file, the main file, the example file. This is an example about an inverted pendulum system, and the corresponding FIS file that is related to the example. This package is also accessible through the ResearchGate website. The main file that should be used is FFIS.m. This function evaluates fractional fuzzy inference systems. Its role is similar to the eval.fis.m, a function in the Matlab software. So let's first recall eval.fis.m. The data that should be entered into the eval.fis is the crisp input values to the system and the fuzzy inference system that has already been built and loaded by the name of FIS. By the use of this data, eval.fis gives us the defuzzified outputs. For example, suppose that we have built a fuzzy inference system and stored it by the name of tipper. Then, for using eval.fis, we first should load the fuzzy inference system using the command readFIS. Then, the input values to the system should be specified. In this example, the system has got 2 inputs. The eval.fis evaluates the fuzzy inference system and gives us the defuzzified output. To use the eval.fis.m, the following steps should be taken. Design the fuzzy inference system and save it by a name, for example, FIS.FIS. Load the FIS, the fuzzy inference system, by the command readFIS. Use the function eval.fis.m to get the output for given inputs. The syntax of the mfile function ffis.m is very similar to that of eval.fis.m. This function converts the typical fuzzy inference system to its corresponding fractional fuzzy inference system, evaluates it for input values in inputs, and returns the resulting output values in the output. The functional indices and the operating mode of fractional FIS take place in the cell array FITs. Therefore, the data should be entered into FFIS.m is the inputs, the fuzzy inference system, and the cell array FITs by which the operating mode and fractional indices are determined for the system. And FFIS.m gives us the output. To use FFIS.m, the following steps should be taken. Design the fuzzy inference system and save it by a name. Load the FIS by the command readFIS. Determining the fractional indices and the operating mode of fractional fuzzy inference system in the cell array FITs. And finally, use the function FFIS.m to get the output for given inputs. Let's compare two mfile functions, FFIS.m and eval.fis.m. Both functions need a fuzzy inference system built in advance. Then the fuzzy inference system should be loaded by the command read FIS, and then the cell array fits should be filled in. By the cell array fits, FFIS.m is given the operating mode and fractional indices of the fractional fuzzy inference system. This step does not exist in eval-FIS.m because typical fuzzy inference systems are single mode and their fractional indices are always identical to unity. The last step is the same for both M-file functions. Therefore, the difference between these M-file functions is related to the cell array fits that should be determined for FFIS.m but does not exist in eval-FIS. Now we shall explain how to use FFIS.m step by step. First, we should design a fuzzy inference system and save it. Building a typical fuzzy inference system in Matlab software is an easy task. Building a typical fuzzy inference system. There are two ways to build a typical fuzzy inference system through the fuzzy logic toolbox. First, building fuzzy systems using fuzzy logic designer, and the second, building fuzzy systems at the command line. Figure 1 shows building the fuzzy system by the use of fuzzy logic designer. Here, we shall focus on building a typical fuzzy inference system using the fuzzy logic designer drawn from the fuzzy logic toolbox by using the command by the name of fuzzy in the command window. A default FIS emerges. For building your own fuzzy systems, you should determine the inputs and outputs membership functions. The function FFIS.m in the first version has been prepared such that it only accepts triangular and/or trapezoidal membership functions for the output. In other words, in the first version of FFIS.m, there are only two options can be chosen for the type of membership functions of the output: try-mf and trap-mf. However, there is no restriction on the type of membership functions for the inputs. In addition, the function FFIS.m in the first version works only for the fuzzy systems with single output. Then you should determine the properties of the fuzzy system. In the function FFIS.m, the implication and aggregation have been set to minimum and maximum, but the AND method can be selected as minimum or product operator. The defuzzification operator is also optional. It should be noted that the FFIS.m in the first version works for fuzzy systems in which the variables in the antecedent part connect to each other only by the connector AND. Thus, the antecedent part is not allowed to include OR connector. Next, you should determine the fuzzy if-then rule base. The function FFIS.m supposes that the weight of rule has been set to 1, and as was already stated, only the AND connector is admissible in this version of FFIS.m function. The connectors NOT and OR have not been considered in this version. So the weight has been set to 1. Only the AND connector is admissible in this version. The connectors NOT and OR have not been considered in this version. After building the fuzzy system, we shall export the fuzzy system to the folder in which the function FFIS.m and your main program file exists. It can be done by File, Export to File, and then save it by a name, for example, FIS. The next step is to load fuzzy inference system by the command read FIS in our main program. So the first and second steps already explained are common between eval FIS and FFIS. Those who are familiar with the fuzzy logic toolbox will know how to complete these steps. The next step is the most important step, in which the fractional indices and the operating mode of fractional fuzzy inference system are transferred into the function FFIS.m. The fractional indices and the operating mode of fractional FIS are expressed by the cell array FITs, in which value I determines the fractional index of the i's fractional membership function in the consequent part membership functions plane, and form I is the form of the i's fractional membership function. Value I may be a real number in the interval 0 and 1, or a function of x. For example, it may be a constant such as 0.1, 0.7, 1, 0.68, and so forth. It may be also a function, for example, a sine function, which is written in Matlab file in this form. Form I determines the form of the i's fractional membership function in the consequent part membership functions plane. For the first form, or the alpha form, we should write a between two quotes, or simply the scalar value 0. For the second form, or beta form, we should write b between two quotes, or simply the scalar value 1. Thus, each pair, value I, form I, belongs to a membership function in the consequent part membership functions plane. Let's have an example. Suppose that this is the consequent part fuzzy sets plane of a fractional fuzzy inference system with the fractional indices shown in the table. There are 5 fuzzy sets, thus the cell array fits includes 5 pairs of values and forms. Each pair belongs to the membership function of a fuzzy set. NB, NS, Z, PS, and PV. Let's fill in the cell array. For the fuzzy set NB, by looking at the table, the fractional index of its membership function is equal to 0.8. So we should write this value here. Also, it is in the first form, or the alpha form. Then the letter A between two quotes should be written here. We can also write the scalar value 0 instead of the letter A. The FFIS.m also interprets it as the first form. Here, for more clarification, we write the letter A. Similarly, for the fuzzy set labeled NS, its corresponding fractional index value is equal to 0.6, and its membership function is in the first form. So, we fill in the cell array by the value 0.6 and the letter A. The fuzzy set labeled Z has got no arrow, and its corresponding fractional index is a constant equal to 1. Then, in the place of value, we write the scalar value 1. And for the indication of the form of membership function, we can either write A or B. there is no difference. Please refer to the sections 1 and 2 to remember why there is no difference. Similarly, for the fuzzy set labeled PS, its corresponding fractional index is a constant equal to 0.8, and its membership function is in the second form or beta form. We use the letter B between two quotes to indicate that PS is in the second form. We can also use the scalar value 1 instead of the letter B. But for the illustration here, we consider the letter B. In the same way, we fill in the cell array for the fuzzy set labeled PB. Now, let's consider the case where there are functional fractional indices. For example, suppose that the fractional indices of NS, PS, and PB are functions of mu star in these forms shown in the table. We only need to write these functions in the same way we write such functions in the Matlab script environment, but by replacing mu star with x. So let's do it. For ns, we have this function. First, by replacing mu star with x, we have this function. Then we translate it into the Matlab script language that is this form, and then write it in the place of the value of the fractional index for ns in the cell array between two quotes. Note that if you forget to write it between two quotes, then you will get an error. For the fractional index of PS, we do it similar to the previous one, replacing mu star by x, translating it into Matlab script language, and write it in its corresponding place in the cell array between two quotes. The same thing is also done for PB fractional index. There is an important point that should be remarked here. Remember that we said each pair value and form belongs to a specific fuzzy set in the consequent part plane. The question is, how do we know which pair corresponds to a specific fuzzy set? For example, how do we know that value 1 and form 1 correspond to the fuzzy set NB? Maybe the pair value 5 and form 5 corresponds to the fuzzy set NB. So first we should be aware of the arrangement of fuzzy sets in the consequent part fuzzy sets plane. Then we fill in the cell array. Fortunately, we can easily find out this arrangement. A simple example explains it. Suppose that you have built a fuzzy system whose consequent part fuzzy sets plane is in this form that you watch on the screen. It consists of 5 fuzzy sets. Suppose that you have saved these FIS by the name of FIS. Use the command read FIS to load the fuzzy system. Then, in the command window, run the command fis.outputs.membership functions. The result of this command shows you the arrangement of the fuzzy sets in the consequent part plane, listed by 1, 2, 3, 4, 5. This arrangement from up to down corresponds to the left to right in the cell array fits. In this example, the first pair, value 1, form 1, corresponds to the first fuzzy set, number 1 in the top of the list, that is NB. Similarly, the second pair corresponds to the second fuzzy set, and eventually the last pair on the right-hand side of the cell array corresponds to the fuzzy set in the lowest place. Therefore, we could easily find out the arrangement. And now we can fill in the cell array correspondingly. The next remark is that, as explained in the previous sections, in this tutorial, when all the fractional indices are identical to 1, a fractional fuzzy inference system reduces to its corresponding typical FIS. This is also the case here, since the implication is minimum. By setting all the fractional indices to 1, the fractional fuzzy inference system reduces to Mamdani's FIS. Note that determining the form does not important, so X can be either A or B. It doesn't affect the output. This slide shows some examples of filling in the cell array feeds for FFIs in different operating modes and different constant values of fractional indices, and particularly the aggressive mode. There is a question in here that should be answered. The question is, why have you considered two options for determining each form of fractional membership function? I mean, we can write A for indicating that the fractional membership function is in the first form, and we can also write 0 instead of A. The answer is, such an option enables us to find the optimal operating mode of a fractional FIS more conveniently through an algorithm, for example, the genetic algorithm. So the algorithm in its framework can change the scalar values 0 and 1 more conveniently than changing A and B. Finally, the general structure of a program code in Matlab software for applying a fractional fuzzy inference system by using the mfile function FFIs.m may be viewed in this form. In the initialization section, the FIS is loaded by the command read FIS. The cell array feeds is filled in, and in the main section, the function FFIs.m is called. For your convenience, this table has been made to show the configuration of FFIs.m. This table can be helpful when you apply the function FFIs.m. Some more advanced versions of the function FFIs.m are released in the future, which will have more optional features, so stay tuned for more updates on the package of FFIs.m. Indeed, anybody who would like to develop this package is welcome. In addition, if someone has got any idea in this regard, they can share with us through the contact links. Finally, the comparison between fractional FISs and typical FISs that has been being completed since the first section in this tutorial is finalized here. I hope you have found this tutorial helpful. For any question, feel free to contact me through the email. Thank you very much for your attention choosing this tutorial and your interest in fractional fuzzy inference systems, the new generation of fuzzy inference systems.